We've looked at weighted least squares, which is an extension of ordinary least squares. You might recall that ordinary least squares is something called BLUE. It's the best linear unbiased estimator when the noise is white noise. But even when we had autocorrelated noise, ordinary least squares is still what I called GLUE. It's a good linear unbiased estimator. And we can revise our error estimates to take autocorrelation into account, which is something we went into in our last lesson. There is, however, a method which is BLUE. It's the best linear unbiased estimator, even when the noise is autocorrelated. It's called general least squares, or GLS. Let's let V sub alpha beta be the variance-covariance matrix of the noise. Let's define a metric tensor as its matrix inverse, even when it's not diagonal, that is, when there's no autocorrelation. That's what we did with weighted least squares. We called it the metric tensor. We also called it the weight matrix. And it was diagonal because the variance-covariance matrix was diagonal. Now we have to recognize that with autocorrelation, the variance-covariance matrix will not be diagonal. It'll have off-diagonal elements. So its matrix inverse, the metric tensor or weight matrix, will also have off-diagonal elements. Well, in that framework, we will find that the procedure for doing general least squares is theoretically a very simple extension. Computationally, it gets a lot more complicated. It's best to let computer programs do it for you. But theoretically, there's not a whole lot that's new here. Let's define the S matrix. We will define it as we did before as the weighted inner product of trial vectors with trial vectors. Do bear in mind that the weight matrix or metric tensor now has off-diagonal elements. We will define dual trial vectors, with the dual trial vectors being the inverse of the S matrix times the trial vectors. Then the general least squares parameter estimates are just what they were before. They are the weighted inner product of dual trial vectors with data values. And just as before, the variance-covariance matrix of the parameters themselves is the inverse S matrix, which serves to underscore the importance of the S matrix and of its inverse when doing least squares regression of all kinds. Now, by the way, it's usually more convenient and plenty good enough to do ordinary least squares and apply an autocorrelation correction. But there are some cases in which general least squares is customary and comes in right handy. One is something called mixed effects models, which are usually analyzed in a very different context, but really they amount to general least squares. Another example is called Kriging, an extraordinarily useful procedure in many cases that, again, when you work out the nitty-gritty, basically boils down to general least squares.